Hello everyone. I'm excited to present our work, a new deterministic method for estimating 6D object pose confidence regions. Here is the overview of our proposed method. First, we use a deterministic regression network to predict the initial distribution for each key point. Then, we apply inductive conformal prediction to get 2D key point confidence regions. Finally, based on uncertainty propagation, we deterministically propagate these 2D regions to the 6D pose space. For key point prediction, we use a transformer-based direct regression network. We train this model with a negative log likelihood loss, which enables it to output key point uncertainty directly. Finally, this network maps an input image to Gaussian distributions. ICP is a framework that produces statistically guaranteed key point confidence regions, ensuring they contain the true value at a user-specified coverage rate. To apply this, we propose a nonconformity function which measures the difference between a new sample and the calibration set. Then, by substituting this score into the ICP, we can compute the final confidence region for new sample. Next, we need to propagate the key point uncertainty into the 6D pose space. However, the common sampling-based approach has the following issues. First, it has slow speed because the computation time increases linearly with the number of samples drawn. Second, it can be inaccurate. PNP solvers that use a minimal set like P3P often produce low-quality pose samples. And finally, this leads to overly large regions. The convex hull of these noisy pose samples unnecessarily expands the final confidence region. To deterministically propagate the uncertainty, we model the PNP solver using the implicit function theorem, IFT. First, we consider the PNP solver as an implicit function g that maps 2D key points x to a 6D pose y. This function is defined by minimizing an objective function. At the optimal solution, the derivative of this objective function with respect to the pose y must be 0. This is the stationary condition. We reformulate this stationary condition as our IFT constraint function f. Finally, by applying IFT to this constraint, we can analytically compute the Jacobian of the PNP solver. This Jacobian describes how the output pose is affected by changes in the input key points, allowing us to directly propagate the uncertainty from the 2D key point regions to the 6D pose space. The final output pose confidence region is an ellipsoid in the 6D pose space, which covers the ground truth at our specified probability. We evaluated our method on two datasets, speed and LMO dataset. For our evaluation, we use three key metrics. First, key point coverage rate measures how often our 2D regions contain the ground true key points. Similarly, 6D pose coverage rate measures this for the ground true 6D pose. Finally, confidence region volume evaluates the tightness of our prediction. Our method is significantly more efficient, with a lower inference and propagation time. Furthermore, we achieve superior 2D key point detection accuracy, outperforming competing methods. Regarding the 2D key point confidence regions, our method's empirical coverage rate is approximately equal to 1 minus epsilon. Meanwhile, our approach doesn't produce the overly large confidence region radii typical of heatmap-based methods. For the pose confidence regions, the sampling method's coverage comes at the cost of excessively large volumes. The not applicable here indicates that all of its regions exceeded the evaluation threshold. In contrast, our direct method successfully maintains a coverage rate near the target of 1 minus epsilon. Meanwhile, as shown in the CDF plot for rotation volume above, and the box plot for translation volume below, our method's volumes in blue and purple are significantly smaller than the sampling-based approach in green. These mean volume results in the table are consistent with the distribution plots from the previous slide, confirming that our method reduces the confidence region volume. Next, we provide some qualitative visualizations of our confidence regions on both the LMO and speed. Thank you for your attention. That's all from me.